All right, welcome back to the deep dive. For this Science Corner, we're going to be taking a closer look at something that most of us probably see every single day,
Yeah.
but maybe don't give too much thought to, and that's sodium vapor lamps.
I think a lot of people, they probably just call them streetlights.
Yeah, the ones with that kind of yellowish glow.
Exactly, exactly.
So we're going to be doing a deep dive into a pretty cool technical report that we found. It's actually Technical Note 59414
Oh, wow.
from the National Bureau of Standards. So now it's NIST.
Yeah.
And this report goes into great detail about high-pressure sodium discharge lamps. You know, the thing is, they were originally trying to use these lamps as like a standard for luminous flux. What we're going to try to do today is go a little bit beyond just the basic explanation of how these things work. We really want to unpack the science and the technology that goes into making these lamps so effective.
It's fascinating how something that seems so simple can have such a deep scientific background.
Right. So
Yeah, why sodium?
what makes sodium so special when it comes to making light?
Well, it all goes back to the way atoms work, right? So you have these electrons whizzing around the nucleus of an atom,
Okay.
and they can only exist at very specific energy levels. Think of it like a staircase.
All right, so you can only be on one step at a time.
Exactly, yeah. No hovering between steps. Now, when you add energy to the system, let's say by running an electrical current through some sodium vapor, those electrons can jump up to a higher energy level, but they don't like to stay there.
So they're kind of unstable at the higher level.
Exactly. They want to get back down to their original lower energy state, and when they do, they release that extra energy as a photon.
Which is light, right.
Precisely. And the color of that light depends on the energy difference between those two levels that the electron jumped between. And it just so happens that sodium has this one particular electron transition that releases a photon with a very specific energy, which corresponds to a wavelength of about 589 nanometers. And that wavelength, my friend, falls right in the yellow part of the visible spectrum. So that's why sodium vapor lamps give off that characteristic yellow light.
Interesting. So this is built into the atom itself, the color that we see.
It is.
Now, the report we were looking at, it talks a lot about high-pressure sodium lamps, which are also known as HPS lamps.
Right.
So what's so special about high pressure? And why were these HPS lamps such a big deal when they came out?
Well, think about it. High-pressure sodium lamps, they came on the scene in 1965 thanks to Loudon and Schmidt. And really, it was a major leap forward, especially when you think about efficiency.
Yeah, because I was reading in the report that the HPS lamps can have a luminous efficacy of up to 150 lumens per watt.
They can. That's a big number.
Yeah. Can you explain what that means, though? Because I don't really know what lumens per watt means, practically speaking.
Right. So lumens per watt, it's basically a measure of how good a light source is at converting electricity into visible light, the kind of light we can actually see. So a rating of 150 lumens per watt, that's really good, way better than a typical incandescent light bulb.
Okay.
Which, those old school ones, they only get around 25 lumens per watt.
So 6 times less efficient.
About that, yeah. And even when you compare it to other types of discharge lamps, like high-pressure mercury lamps, which are more efficient than incandescent bulbs, but they only manage about twice the efficacy. And even modern alternatives, like your metal halides and your fluorescents, they're still less efficient than HPS. They're closer, but HPS is still about 50% better.
Gotcha. So you get more bang for your buck, so to speak.
Exactly.
More light for the same amount of electricity. That explains why they were used so much for street lighting, I guess. And even today, the report mentions there's still research being done to improve them.
Oh, yeah. There are always ways to make things better, to tweak the materials, to refine the engineering.
So it's not like a dead-end technology, even though it's been around for a while.
No, not at all.
Now, the report does hint that there were some challenges in actually building these lamps.
Right.
Especially because sodium vapor, when it gets hot, it can be really corrosive.
Oh, it is. Very corrosive. And working with sodium at those temperatures, it's a tough challenge. Like ordinary glass, it just wouldn't hold up. The sodium would eat right through it. So they needed something special. And that's where translucent polycrystalline alumina comes in.
PCA?
PCA, exactly. And it was a game changer.
So what makes PCA so good at handling that hot sodium vapor?
Well, first off, it's incredibly resistant to chemical attack. Unlike glass, it can withstand the corrosive nature of sodium at high temperatures for a very long time. Plus, it's also really good at letting light through. You get over 90% of the visible light that's generated inside that arc tube actually escaping the tube.
Hmm.
And on top of that, PCA can handle some serious heat, like we're talking temperatures up to 1600 degrees Celsius. And you need that kind of heat resistance to get the sodium vapor pressure high enough for efficient light production.
Wow, so the PCA tube is like the heart of the lamp where all the action happens.
It is.
But what about the other parts that the report mentions? Like, there's something called an outer glass envelope.
Right. That outer envelope, it's there for a few reasons. Mainly, it acts like insulation for the PCA tube, which is running super hot, so it helps keep the temperature stable and protects it from outside world.
Okay.
But that outer envelope, it has its own limits. It can only handle temperatures up to about 400 degrees Celsius. And there's also this little thing called a getter inside the outer bulb. It's basically a chemical sponge that traps any impurities that might get released from the lamp components over time. And this helps keep the vacuum inside nice and clean. And it also helps with the stability of the electrical discharge in the arc tube itself.
So it's like a little cleanup crew inside the lamp.
That's a good way to put it.
And speaking of the arc tube, I noticed that the report mentions it's smaller than the tubes in some other types of lamps, like mercury lamps.
Yeah.
And there's no starting electrode inside.
Yeah.
So how does the electrical arc actually get started?
Oh, well, that's a clever bit of engineering. You see, since there's no internal electrode, the HPS lamp uses a special starting circuit that's built into the ballast,
Okay.
which is that external box that controls the lamp's power. So this circuit, it sends out these really short, low energy but high voltage pulses
Okay.
across the electrodes at each end of the arc tube. And these pulses are enough to ionize some xenon gas that's also inside the tube.
So the xenon is what gets the party started.
In a way, yes. The ionized xenon creates a path for the main electrical discharge to follow. And once that's established, it starts heating up the sodium and the lamp really gets going.
And then the whole thing starts to glow. And speaking of glowing, the report mentions that when an HPS lamp first turns on, there's like a color shift that happens as it warms up.
Yes, the warm-up show. At first, when you flip the switch, you get this faint bluish-white light because the initial discharge is mostly happening through that xenon gas.
Right.
But as the arc tube heats up, things start to change. You've got a little bit of mercury in there, too, usually as part of a sodium-mercury amalgam.
Okay.
And as the temperature rises, the mercury vapor pressure starts to climb. But then the real star of the show, the sodium, starts to get hot enough to vaporize. And as more and more sodium atoms get excited by that electrical current, the light shifts from bluish-white to that bright yellow that we associate with sodium lamps.
So it's like a gradual transition, not an instant change.
Exactly. And as it reaches its full operating temperature and those vapor pressures stabilize, the spectrum broadens a bit and you end up with a more golden white light. Still has those strong yellow sodium D lines, but you also get some reds and greens mixed in.
Wow, so there's a whole lot going on inside that lamp as it warms up. It's like a little symphony of elements, all playing their part.
I like that.
Now, once the lamp is fully warmed up and running, what are the main things that determine how bright it is and the exact color of light it emits?
Well, there's a whole bunch of factors that come into play, all interconnected. But the big ones are the vapor pressures of the sodium and mercury inside the arc tube. And those pressures, they're determined by a few things, like the ratio of sodium to mercury in that amalgam.
Okay.
How much of that amalgam is there?
Right.
And really importantly, the temperature at the coldest spot on the arc tube, which is where the amalgam hangs out. Then you've got the xenon pressure to consider and the physical dimensions of the discharge tube itself, like the diameter, the length, the thickness of the PCA walls, the materials used. Oh, and we can't forget about the tube wall loading. That's how much power is being dissipated per unit area on the tube wall. And then there's the electrode design and the materials they use to make sure that electrical discharge happens smoothly.
So it's like a really complex recipe with
Nice.
all these different ingredients.
It is quite a recipe.
And I think I saw in the report they actually gave some typical operating pressures and dimensions for a standard 400-watt HPS lamp.
Yeah, they did. I believe for a 400-watt lamp, you're looking at a sodium vapor pressure of around 10 to the third pascals, a mercury vapor pressure of about 8 times 10 to the fourth pascals, and xenon at about 2 times 10 to the third pascals.
Okay.
And the arc tube, it's not very big. Inner diameter of about 7.5 millimeters, electrode spacing around 82 millimeters, and the PCA wall, it's only about 0.6 millimeters thick.
Wall loading somewhere around 20 watts per square centimeter. So it's pretty remarkable how they pack so much into such a small space.
Yeah, and you mentioned the amalgam earlier.
Right.
And I think you said there's a reservoir of it somewhere in the lamp. How does that help keep the light output stable over time?
The amalgam reservoir. It's usually located at one of the cooler ends of the arc tube, and it acts like a little refill station. You see, during operation, some of that sodium and mercury evaporates from the amalgam to participate in the electrical discharge and make the light.
Okay.
But over time, you're going to lose some of those atoms just through various processes. That's where the reservoir comes in. It has this extra supply of sodium and mercury that can replenish what's lost from the discharge. This helps keep those vapor pressures stable, which in turn means a more consistent light output and a longer lifespan for the lamp.
So the temperature of that cool spot where the reservoir is, that's pretty crucial, right?
Absolutely. It directly affects those vapor pressures, which in turn dictate the spectral power distribution of the light, meaning the color. Right.
Precisely. The report actually highlights the importance of what they call self-reversed sodium D lines. It's a specific feature in the sodium emission spectrum that plays a big role in both the color rendering of the light and the overall efficiency of the lamp.
Self-reversed D-lines, huh? That sounds pretty complicated.
It is, but we might have to save that for a future deep dive.
Sounds good to me.
Yeah.
But yeah, the report mentions that the typical operating temperature for the amalgam reservoir is between 600 and 750 degrees Celsius, which, I mean, that's still really hot for the cool spot, you know?
Oh, yeah, it is. And any stray radiation that bounces back from the main discharge can heat that reservoir even more. And that can mess with the vapor pressures and the light output. That's one reason why you need a really stable power supply for these lamps. Any fluctuations can lead to inconsistencies.
Right. Because I did see in the report that if the sodium vapor pressure gets too high, maybe because the cool spot is getting too hot, it actually changes the shape of those self-reversed D-lines.
It does. And they even mention specific mole fractions of sodium in the amalgam for getting the best performance out of a 400-watt HPS lamp.
Yeah, I think they said for a 400-watt lamp, the ideal mole fraction of sodium is around 0.70 when the amalgam temperature is about 640 degrees Celsius.
Yeah, that sounds about right.
So they really did a deep dive into the nitty-gritty details of how to get the most out of these lamps.
They did.
Now, let's switch gears a bit and talk about where all that electrical energy that goes into a 400-watt HPS lamp actually ends up.
Okay.
Like how much of it gets turned into light, how much is lost as heat, that kind of thing.
Right. So in a typical 400-watt HPS lamp, you're going to get about 50 to 60% of that energy converted into radiant energy. And of that, about 118 watts ends up as visible light, which is what we actually see.
Okay.
Then you've got about 80 watts that gets emitted as infrared radiation.
Which is heat, right.
Exactly. And a tiny bit, about 2 watts, is ultraviolet. And then there's a small amount, maybe 5%, that's lost as heat at the electrons themselves due to their electrical resistance. But overall, most of the energy does go towards making light, which is why these lamps are so efficient.
Yeah, that's pretty impressive. Now, we've talked about sodium and xenon playing a role in these lamps, but what about mercury? Why is that in there if sodium is the one that's actually making most of the light?
Good question. So while the sodium gives us that yellow light, both xenon and mercury are important behind-the-scenes players. We already talked about how xenon is crucial for starting the arc, and it also helps protect the electrodes from the corrosive effects of that hot sodium vapor. But mercury, its main job is to boost the operating voltage of the lamp. It does this by basically slowing down the electrons in the arc plasma. And having a higher operating voltage, it makes it easier to match the lamp to the ballast, which is that external power regulator. And that helps the whole system run more efficiently and stably. And it's interesting because the light that comes directly from xenon and mercury, it's pretty negligible in terms of the overall visible output. Their main jobs are in getting the discharge going and making sure the electrical characteristics are right.
So it's like they're the support team for the sodium, which is a lead singer.
Exactly, a well-coordinated team.
So with all these complex interactions happening inside the lamp, how stable is the light output over its lifetime?
Well, HPS lamps are actually known for being pretty good at maintaining stable lumen output. Among all the HID lamps, they're some of the best.
Really?
Oh, yeah. And I think the report gives an example for a 400-watt lamp. It says it can maintain about 98% of its initial light output after about 17% of its rated life, which translates to around 4,000 hours of operation. And even towards the end of its life, which can be as long as 24,000 hours, it still puts out around 73% of its original brightness. That's not bad at all.
No, that's pretty good. So what are the things that eventually cause these lamps to die?
Well, it usually comes down to a gradual increase in the operating voltage over time. And this can be caused by a few things, like changes in the composition and temperature of that sodium-mercury amalgam.
Okay.
Also, there's always a little bit of sodium loss from the arc tube, and then over time you get stuff sputtering off the electrodes and depositing on the inside of the PCA tube, and that makes it darker, which increases the temperature, which then affects the vapor pressure, and it's all connected.
Mhm.
And that can lead to a higher operating voltage. And the light output can also go down because of that electrode darkening. And sometimes you get these deposits of alumina from the PCA tube that end up on the inside of the outer bulb, and that can block some of the light too. And then there's that slow sodium loss, which changes the sodium to mercury ratio. And eventually, the ballast just can't keep up. It can't provide enough voltage to sustain the arc, and the lamp gives out.
So it's kind of a death by a thousand cuts, just gradual wear and tear over time.
Yeah, pretty much.
Now, this report that we've been talking about, it's actually a National Bureau of Standards technical note, and they were specifically looking at characterizing these HPS lamps to use them as standards for measuring luminous flux. Well, why was that so important for them to do?
Well, you see, for a long time, NIST, back when they were the National Bureau of Standards, they used calibrated incandescent tungsten lamps as their main reference for measuring light. And that worked pretty well back when most lighting technologies were similar to incandescent lights in terms of their spectrum. But when discharge lamps, like HPS lamps, started becoming more popular, well, they have a very different spectral power distribution compared to tungsten, so making accurate comparisons became a lot harder. And they needed a way to ensure accurate light measurements across the whole industry, so they needed standards that were specifically calibrated for these newer types of lamps. And the 400-watt HPS lamp, it was a good candidate because it was pretty efficient and had a fairly stable light output, especially compared to some other discharge lamps at the time.
So they were basically trying to create a benchmark that everyone could use.
Exactly. They wanted something that manufacturers and testing labs could all rely on to calibrate their own equipment so everyone was on the same page. And the report goes into a lot of detail about how they went about selecting the most stable lamps to use as these standards.
Yeah, it sounded like a pretty rigorous process. What did they actually do?
Well, first, they would take these brand new lamps and run them for about 100 hours straight. They called this the seasoning period, just let those initial characteristics settle down. Then they would carefully monitor the light output for several hundred hours more using some really precise equipment.
Wow.
And they had very specific criteria for what made a lamp stable enough to be a standard. Like, the light output couldn't vary by more than 2% per 100 hours during a certain testing period. The spectrum had to stay pretty much the same. And transition time between that initial mercury discharge and the stable sodium discharge, that had to be consistent too. So only the lamps that met all those requirements made the cut.
That's pretty intense.
Sure.
And they even built a special setup for these measurements, right? With like a giant integrating sphere and a spectroradiometer.
Yeah, they did. The integrating sphere, it's basically a big hollow sphere with a super reflective inner surface.
Okay.
And it captures all the light from the lamp, no matter which direction it's going in, and it diffuses it all around. And this lets them accurately measure the total amount of light coming from the lamp.
Makes sense.
And then the spectroradiometer, it's this instrument that measures the intensity of light at each individual wavelength across the visible spectrum. So it tells you exactly what the spectral power distribution looks like.
Wow.
And by comparing the measurements from the HPS lamps to those from calibrated incandescent lamps, which they already knew the luminous flux of, they could figure out the luminous flux of the HPS lamps. They even had to apply a correction factor to account for any differences in how the two types of lamps absorbed light within the integrating sphere. So they were being really thorough.
It sounds like they were.
Oh, yeah. They really wanted to make sure those measurements were accurate. And the report actually has tables showing the luminous flux measurements of different HPS lamps over time. And you can really see how some lamps were much more stable than others.
I see. And they also tested how repeatable the lamps were when it came to relighting them.
Right.
Why was that important?
Well, if you're going to use a lamp as a standard for calibrating other instruments, you need to know that it's going to give you the same amount of light every time you turn it on. If it's inconsistent, that introduces a lot of uncertainty. So they did these tests where they would turn the lamps on and off multiple times and measure the output. And for the lamps that met their stability criteria, the light output was usually within plus or minus 1% of the average value.
That's pretty consistent.
Oh, yeah, very consistent. And that kind of repeatability was crucial for them to be confident in using these lamps as standards.
Well, this has been a fascinating deep dive into the world of sodium vapor lamps. Thanks to this really comprehensive report from the National Bureau of Standards, we've learned a lot. From the basic atomic physics of how they work to the complex engineering that goes into making them, it's amazing to see how much science is packed into something as seemingly simple as a streetlight.
It is, and it's a testament to how scientific understanding and engineering ingenuity can come together to create something that's so practical and widespread. I mean, these lamps have been lighting our streets for decades, reliably and efficiently.
So next time you're walking down the street at night and you see that familiar yellow glow, maybe you'll take a moment to think about all the physics and chemistry happening inside that bulb. And maybe you'll even consider how newer lighting technologies, like LEDs, are building on this foundation, pushing the boundaries of how we turn electricity into light.
That's a great point. It's always fascinating to see how technology evolves, how we take what we've learned and keep pushing forward.
Well, on that note, I think it's time to wrap up this science corner. But hopefully this has sparked your curiosity to maybe learn more about other types of discharge lamps or even dive into the history of lighting technology itself. There's a whole world of illumination out there waiting to be explored.
Could have said it better myself.
Until next time, keep on diving.
Keep exploring.